Mashelkar was a product of ICT Mumbai. Huh?
Yes. It is bachelor's as well as PhD, both from ICT.
Yeah. Your visit to NIIST probably maybe long years ago, eh? Or...
Yeah, I will tell you when. It's been around 2012-13, about 10 years ago now.
Okay. So Rajan, get ready. You have a few more seconds to go.
Yes, sir. Already it's. So we have that YouTube live also. Already alive. It's. YouTube is also there, sir. So students will be participating to YouTube and regular staff through the MS Teams.
Okay, great. So, shall we start then?
Yes, sir, we can start.
Professor Pandit, shall we begin?
I think he's muted.
Yes. So
we have that YouTube live also.
Okay, then.
YouTube is also there. Students will be participating.
Professor ANIRUDDHA Pandit, Vice Chancellor, Institute of Chemical Technology in Mumbai. Dr. TPD Rajan, my dear colleagues, students, other members of CSIR-NIIST family, friends, ladies and gentlemen, good afternoon to all of you. You know the importance of today. We are celebrating the National Science Day every year on February 28th. I think all our institutions in this country invariably organize various programs to commemorate the most historic day when C.V. Raman, announced his discovery of Raman effect, and also to celebrate all the accolades that he has brought to this country. And this country is known for Raman, especially the science of this country is known for Raman and Raman effect and Raman's legacy of science, particularly physics. We Indians are really very proud of it. Every moment we would like to cherish. We would like to pass on the happy, time and memories to our younger generations, to the public. And I am sure that this is going to strengthen the role of science and the relevance of science and what science has done to the society. So to celebrate with us today, we have a great personality from this country, Professor Pandit. A few days ago, I contacted him with a request, and knowing Professor Pandit, I was very confident that he will agree to my request, and that is what happened. So, and not only that, he wanted very much to come to Trivandrum to meet all of us here, to meet the students, to talk to them face to face. And it was almost done, but then suddenly, people like Professor Pandit is always in demand. So he had, an important, assignment today to address the, Doordarshan, that also to tell the public on the importance of science, popularization, the need for popularizing science, and creating public awareness among the common man, the layman, and also the early students, younger students. And because of that, he could not come, but he said that whenever he has another opportunity to come to Trivandrum, he will come. So, but he is with us through the electronic medium. So on behalf of all of my colleagues here at the outset, let me extend a very, very warm welcome to Professor Pandit for accepting the invitation and finding time to deliver the National Science Day lecture at CSIR-NIIST. So I understand that Professor Pandit had visited this institute early, but sometimes back. And since then, a lot of changes has happened to this institute. Of course, you may be knowing as an enthusiastic researcher and a teacher, you may be knowing the progress happening across the country in various institutions, at least, institutions of your interest. And I'm sure that you must be closely watching the progress and the activities of this institute. And also, I know that you have some connections. Some of your students are here. I know all those kind of connectivity. Just for your information, I would like to say a few things about the institute. I took over 7 years back as the director, and before that I was a scientist here, for long 34 years. I never wanted to move out of this place because I like Trivandrum very much, the institute very much, the people here very much. So after I took over, we have been trying to add, further to what we can to this institute, because the institute is always on a progressive mode, and leading such an institution is a challenge, So because adding on the top is always difficult, So, but with the continuous support of my colleagues, the hardworking, young group of people and senior people, we have been progressing very well in the institute, even for the last 2 years, even though in principle we have lost those 2 years, in terms of, our active activities, life, but still, we could manage very well. And we have done a lot of, appropriate repair to the whatever damage we acquired due to this pandemic. So it is the right opportunity for me to thank all my colleagues for standing, with all their support and hard work. So this institute, it is formed in October 6, 1978 as a regional research laboratory, and then subsequently renamed in 2007 as National Institute for Interdisciplinary Science and Technology. We have 5 major research divisions in this institute, addressing chemistry, materials, environmental science and technology, agro-processing, food and nutrition, and then microbial technology. So these are our main activities. They are all interconnected. Of course, chemistry plays a very central role with material, science and technology division, and all other divisions strongly participate in interdisciplinary activities. And this lab is known for its high quality science and a lot of, publications across the disciplines. And also we are reasonably, successful in translating those knowledge which we have accumulated all over the years to useful technologies and processes, and also for societal uplift. And many technologies have been transferred from this institute, earning significant amount of revenues. So it is I should tell that it is an all-round performance, in the domain of interdisciplinary science and technology. So with this very brief introduction about the institute, I would now like to briefly introduce Professor Pandit. I will not take much time because Professor Pandit is known for many of you to a very great extent. So therefore, I briefly introduce, especially for the benefit of the young PhD students, and some of the master's students and project students who are working with us. As I mentioned, Professor Pandit is currently the Vice Chancellor of Institute of Chemical Technology at Mumbai. You know, this institute is one of the flagship institutions in this country, especially in the domain of chemical engineering, process engineering, etc. This institute has a great legacy of having so many leaders who were really controlling the entire process engineering, chemical engineering, technology, and related subjects. For example, many of you know Professor M.M. Sharma, who is a veteran and one of the topmost chemical engineer of this country, having worldwide recognition. Professor Joshi, Professor Yadav, and then Professor Pandit. Maybe I might have missed many people in between. These are some of the people who.
Previous DG CSIR, Dr. Mashelkar as well.
Yeah. That I think he was not the Vice Chancellor of the.
He still is a Chancellor. He's not a Vice Chancellor. He's a Chancellor.
Okay. Yeah. I was about to tell about. Yeah, I was about to tell about Professor Joshi. I mean, Professor Mashelkar. I know that Professor Mashelkar, is the product of ICT Mumbai. I'm glad to hear that he is the Chancellor of the institute. So many important personalities have emerged from this institute, and we are all proud of this institute. I was also fortunate to be involved in some small way, with this institute. I know some people there, and some of them were also in our research council and so on and so forth. So speaking of Professor Pandit, he earned his BTech degree from IIT Benares. It is the previously known Benares Hindu University, and then he earned his PhD degree from University Department of Chemical Technology, now ICT. He completed his PhD in 1984, and then he went abroad, and he was in UK Cambridge University for several years, and then 1990 returned to India, and then took a position in ICT. He was instrumental in starting a major activity and a program in the area of hydrodynamic cavitation for intensification of physical and chemical processing application, which is one of his favorite topics, I understand. And Professor Pandit has made significant contributions in some of these domains of chemical engineering, and that is, written over more than 370 world-class publications and several book chapters and patents, maybe 16 odd or even more patents, on his credit. And more than that, he has over 50 PhD students completed PhD under his mentorship, and maybe around close to 100 maybe master students whom he trained. And I'm sure that many of those students are now in many important positions, and his PhD students in many important positions in this country and abroad as well. And there is no need to say that for all his contributions, Professor Pandit have received so many awards. It is obvious that a person of his caliber will deserve all kinds of merits and recognitions. And I just want to sound a few things, like he's one of the best first-class teachers. I know that, and that was credited with INSA Best Teacher Award, and then J.C. Bose National Fellowship and Vishwakarma Medal, and he's a fellow of most of the academies of this country, and also he's a fellow of the World Academy of Sciences. He was elected at the year 2015. And since he's taken over as the Vice Chancellor of the Institute, he has made changes to that place. And one of the most active Vice Chancellors. And prior to that, he was Dean and also Dean of the Research Consultancy and Research Mobilizations. He has vast experience, and all this experience he put together for the overall progress of this institute. He has been the coordinator of many programs, for example, the ICT DAE, Center for Chemical Engineering, and then so many other programs, foreign collaborations of the institute with many countries like France, Australia, Netherlands. He was also coordinating main program of the DST, UGC, and many other activities to the benefit of the institute. He has been serving in advisory role in many of these organizations in this country, especially as the BOG members of many institutions like IITs, IIT Bombay, and many other. And he has been an active industrial consultant to many national and international companies. He has transferred many technologies, many processes, and so on and so forth. So if I want to read, I can still take yes.
Now just appeared.
Yes, sir.
Yeah.
It's
done.
It's visible now?
Yes.
Okay, good. So as the title suggests, that the environmental management, so I'm talking about environment and managing the environment without sacrificing the growth and the progress and the betterment of human life, which all engineering and scientists and technologists essentially aim for. And in my opinion, National Institute of Interdisciplinary Science and Technology, NIIST, is ideally suited to take this particular area as well. And that is what I'm going to dwell upon for the next, let's say, 40 minutes or so. Let me move on to the next slide, and how I'm going to describe this entire option is sustainability and a natural capital. Basically, whatever resources which you are using, these resources are coming from the sun. The only basic energy source which is available to us is in the form of sun, and the same energy source is responsible for giving us the natural capital which is indicated out here, which we call it as an ecosystem. We exploit these resources and that translate those resources into economy, and those economical resources harvesting is carried out through product and services. But there is a limit to it, and this limit essentially is provisioning, regulating, and cultural. Now, all these three things are basic nature of human beings, and they need to be satisfied, and we continuously keep on improving upon it using the resources which are coming essentially from the sun, and these we try to improve upon always in terms of security, whether it is personal or the societal security from disasters. I'm sure you would be in a position to understand the kind of natural calamities which which Kerala has experienced because of the climate change and because of the global warming phenomena. Then we also concentrate on provision of basic materials which are required for good life and good health and good social relationship, whether it is internet or WhatsApp or means of communication. And as a human being given a freedom, it has a freedom of choice and action. But at the same time, that action has a restriction in terms of doing something which is not necessarily harming the entire society or at an expense of an individual. So once you consider this, you really need to look at the status of these resources or the natural capital which we are currently exploiting. And if you look at it, that there are severe constraints on us and severe limitations on us due to over-exploitation of some of the resources. And you periodically keep on hearing these things that in next 20 years time, 30 years time, the petrochemical reserves or fossil fuel reserves are going to get exhausted and we'll have to find a new energy source, so on and so forth. So there is a group of 1,300 odd experts which decided to come together and they decided to assess the current millennium ecosystem, meaning after using this ecosystem, exploiting this ecosystem for a period of last 60, 70 years or so, what is its current status and how this status can result into severe constraints and limitation as a resource for the next generation to come. And what is the scientific basis, at what rate we can start exploiting these, at what rate we can utilize it without really affecting the resource availability for our future generations. If anyone is interested, they can look at that website in detail and learn more about it. Unfortunately, this is what the status of our sacred rivers are, and you can see how the dumping of waste as well as over-exploitation of water, the soil erosion, all these are making a big and huge difference in terms of availability of resources for the future generation. You look at the over-exploitation of the water and a significant reduction in the water table level, especially in the Haryana, Punjab region due to crop as well as agricultural activity, where even though water is available, the type of resources, water resources which have been utilized have resulted into a substantial depletion in the available water resources, and the level or the depth of the bore well keeps on increasing by meters every year. This is some of the examples which you yourself would have experienced. Soil erosion is a major issue. Fertile soil, the upper layer of the soil with rich organic content, which is absolutely essential for the sustaining of agricultural economy of India. If the organic carbon content in the upper soil reduces, then the soil productivity is significantly lost. So we need to do something about it. This is a photograph from Vadodara, and I'm sure Kerala also has experienced significant landslides, significant loss of land as well as loss of upper soil and washing of this particular soil and getting deposited in other parts of the country, other parts of the state. You move on and you look at the various cycles which have been responsible for climate change. Now these cycles, which you can see from here, is the green part, we are relatively okay. Red part, we are actually encroaching upon the limits of the ecosystem, and that beyond the outermost circle, this is started affecting our environment and affecting our climate change. So if you look at it, you will find that in certain cases, the situations are so bad. The situations are so bad that we need to do something about it yesterday, right? We cannot continue with this. The loss in biodiversity the increase in the nitrogen content in the atmosphere, as well as a lack of nitrogen fixation or significant amount of nitrogenous fertilizers being used randomly without supporting phosphorus and potassium fertilizers, which is absolutely necessary for any agricultural commodity growth. Now, one look at this particular concept of World or Earth Overshoot Day. Earth Overshoot Day signifies the quantum of resources which we have used in a year's time and how long it takes for you to renew those particular resources. So if you see in case of India last year, 21, the overshoot day for India was 22nd of August. What it means that whatever renewable resources which are available to us in a matter of 12 months, these resources we have been consuming it in a matter of 8 months. So we are actually borrowing 4 months of renewable resources, and if this current status goes on, I'm sure 10, 20, 30, 40, 50 years down the line, we are going to have severe constraints on the resources. So one needs to look at it, and I will tell you some of the methods which are required for us to look at it and the methodologies which can be adopted. So there are certain external drivers and there are certain drivers which are necessary for an institute. So the external drivers are climate change awareness, government initiatives, rating and labeling scheme, whether it is ISO 14000 or ISO 14010, which really addresses the environmental concerns along with the manufacturing activity and the system as well as the quality of manufacturing activity is concerned, which is ISO 2000. So environmental advocacy, it is essentially awareness. For CSIR, essentially, we need to create a value system. We need to use the branding, the kind of technologies which are coming out from CSIR. People should believe and accept these particular technologies, and that is only possible if we show that our technologies are green technologies, our technologies are sustainable technologies, and they still can compete in the market. So there is a category of sustainability indices which were developed by a Dow company, and this is known as a Dow Jones Sustainability Index, that you start with the regulatory compliance, which is a must do, because these are regulatory compliances which an environmental protection agency ensures that you stick to, results into pollution prevention, which also results into product stewardship. It could be a process stewardship as well, where you see that some of the activities are named after some people. So those activities, those processes are essentially led, and a particular organization or an individual is a steward for that particular activity. I'm sure NIST will also have a certain specific technologies which they can name off, and they can steward these particular technologies. So when you follow this, you essentially are following along the line of sustainability index. So look at it this way, that you have innovation and product process resulting into technology and innovation. Then you have, then you have reduction into resources productivity, that is you maximize the production using the same resources, and the process intensification or more from less or more from the same. All these cliches or all these buzzwords are essentially forms a part of sustainable strategy. You continue with this, then you get a reputation for stewardship and social responsibility, which results into activity growth. So growth of any organization, be it CSIR lab, be it industry, essentially depends upon its reputation, stewardship, and the innovation and product processes and design technology designs, which results into the name. And this then is essentially needs to be now accounted for with climate stabilization as a constraint. So we need to practice all these four while keeping in mind the constraints of climate stabilization. So the approaches towards sustainability involve energy efficiency and eco-efficiency, and I'll talk about these definitions in detail a bit more later. A life cycle analysis, I'm sure many of you have heard of this particular phrase as well as terminology. So typically when CSIR labs and technology is being marketed and where you try to sell this particular technology, the first question you get, whether it is competitive, how far does it compare or does it benchmark with the international technologies or international prices. But at the same time, you also need to consider whether the technology which you are promoting is sustainable or not. Now that could be a selling point, and it is going to happen. Now, I'm sure people who can afford are now going for green vegetables or green products, and you start getting labels of that as well. People who can afford it will start paying more, which is essentially paying for the environmental cost, that is protecting the environment. So we need to look at the product synergy and the concept like circular economy, biomimicry. And nature is the best converter or a conversion maker as far as resources are concerned. It doesn't waste any resources. A product coming from one process becomes a starting material for the subsequent process, and the economy survives. And this is what we call as circular economy. So nature has been practicing this circular economy quite regularly for hundreds and thousands of years and still able to sustain itself. Whereas we, under our greed, are exploiting resources without bothering about tomorrow, which cannot sustain itself. But it is possible for you to think intelligently and think in terms of ecological networks. And I'll give you some of the examples of these ecological networks in due course of today's lecture. One concept which I'm trying to put forward is we have been doing energy balances. But in addition to energy balances, if we can look at exergy balance, exergy is the same as energy in terms of its unit, but it also specifies the quality of energy. That is, if I have the same enthalpic content of a steam, I can use it for many operations, whereas the enthalpic content of warm water, I cannot use it other than maybe for bathing purposes. So the quality of the steam, which is essentially a difference in the surrounding conditions, surrounding temperatures and pressures, and the actual conditions at which temperatures and pressures at which the energy resource is available, needs to be looked at, and that is what is called as exergy. So this exergy is defined as units are exactly the same as enthalpy units or energy units. So it measures the distinguishability or thermodynamic distance from the surroundings. Distance from the surroundings means how much away it is from the equilibrium. The more away it is from equilibrium, more energy will be able to extract from it, and it will be of a higher quality. For example, electricity is the best form of energy which is available to you, because you can use this particular electrical energy for multiple operations. You can use it for heating purposes, you can use it for mobility purposes, you can use it for drying, you can use it for cooking, you name it, and you can utilize this form of electricity, this form of energy, which is electricity. So this concept essentially captures the first law, which is the energy conservation law, but also the second law of thermodynamics, which takes into account the quality of the energy. So it essentially indicates the difference between heat and work or the form of energy. I move on to this, and these are essentially the definitions of physical exergy. H is of course the enthalpy, and S is the entropy, and the temperature difference. At what temperature the energy is available, that makes a big difference in terms of physical exergy. Thermal exergy again is the temperature. TR is the surrounding reference temperature, and TO is the temperature at which you are carrying out a conversion operation. And chemical exergy essentially gives free energy, base energy, which can be exploited while carrying out conversion. So let me show you, this is the way you express exergy analysis or energy analysis, which is done through Grassmann or a Sankey diagram. And if you find exergy analysis shows most losses in the rejected heat. So if you look at it, when you use coal and convert it into electricity, only 37% of the energy, original energy associated with the coal gets converted into electricity. So the quality of energy when you convert coal into electricity has significantly increased, but in the process, about 63% of the exergy, the original energy associated with the coal, has been wasted. So this indicates that the essential problem which you are going to face in future is the loss of exergy. So your every process which you carry out needs to be looked at not from energy conservation point of view. Energy conservation is going to happen anyway because energy cannot be destroyed, cannot be created. But at the same time, when you are using this particular energy, what is the exergetic loss which is occurring? So if you use an electrical geyser for, let's say, heating up water for bathing purposes, then its energy efficiency is more than 97-98%. Whatever electricity which you have used, everything gets converted into hot water which you use for bathing purposes. But if you look at the exergy or exergetic efficiency of this electric geyser, the exergetic efficiency of electric geyser is only about 4%. That means you could have obtained hot water by many other means using a lower quality energy, but instead of that you decided to use a high quality energy. In the process, you are losing out on exergy. So if you look at this, exergy analysis tells you exergy identifies losses in the equipment. It also tells you which are the areas where you need to concentrate on so that you are in a position to reduce the exergetic loss which is required. So if you look at eco-efficiency and the bottom line is the profitability which we talk about. So eco-efficiency is the ratio of value of delivered product per unit resource input. If you use a certain amount of energy and you convert it into a product and the product has a certain energy associated with it, in what form that energy is being translated, in what form these kilowatt hours of energy has been converted into your product cost in terms of sale price. So if the processes are simpler, fewer resources are going to be required, less of waste is going to be generated, and you will essentially get a cleaner product. So if you look at ISO 14000 certification criteria and the methodology which is followed for the same, you will understand what I am talking about. But lower investment, fewer resources also results into less cost, lower investment. Because the processes are simpler, you encounter less of risk and which results into a greater value. So this is where we call it as a systems engineering approach. So let me just tell you what the systems engineering approach is. Initially, when any CSIR lab is interested, except probably NIRI, they will be developing processes, inputs, converting those processes into a product, and then distribute that product. So that is the enterprise or the process enterprise. You go one step ahead, draw one more circle, and you will find that then now you start thinking in terms of recovery and recycle or disposal. And if you go on the back side, on the left hand side, the process prepare inputs requires extraction of raw material, which requires flows and services, and it starts affecting the other factors such as life cycle, economy, and ecosystem. What I'm trying to indicate, the second law tells you that you try to bring in any product. The product is essentially equivalent to bringing a certain order into the system. Now, if you are bringing in order into one system, definitely disorder somewhere else has to increase. Now, this disorder manifests itself in the form of environmental impact. Now, one needs to look at it very, very seriously. So you look at the life cycle analysis criteria, you aim to consider the process, all the processes from cradle to grave, right? You need to have data for each stage of the life cycle. That is, what is the energy, what are the materials, what are the emissions, and what are the standards which are devised. And you keep on expanding the boundary of your analysis. The more or the larger the boundary, data acquisition becomes difficult, assumptions become important, and having an accurate data to assess it becomes more important. You might have heard about these standard examples which are given, whether a paper bag is better than a plastic bag or vice versa. And if you look at the actual analysis of it, you will find that the plastic bags are much better than the paper bags, provided you go one step ahead and learn to find out or learn to understand what you are going to do with that particular plastic. Once you have extracted carbon from the earth, now then it is absolutely necessary for you to have this particular carbon fixed and not let that carbon go into the atmosphere in the form of greenhouse gases, which is what is responsible for climatic change. So you have so these debates which have been going on, whether corn should be used for ethanol or ethanol should be utilized in the gasoline. Now all these debates are going on, and what I am going to do is I am going to just put forward some of these issues in front of you for you to think about it. So the resource aggregation, so what you require to do and require to understand and require to calculate is industrial or ecological cumulative exergy consumption. Since energy and exergy has the same units, you can start with the energy consumption for any particular process, but while consuming that energy, if you bring into account the quality of energy which you are carrying out, it will also address the issue of exergetic loss or cumulative exergy consumption. So if you look at it this way, so you have standard industrial process, natural resources are put in with certain exergy, products are obtained. But you go one step ahead, this is essentially industrial cumulative exergy consumption. You want to bring in environment, then you need to look into ecological input that results into ecological cumulative exergy consumption. So you go back and look at the ecology of these processes which you have adopted, and then these processes will tell you whether these processes are sustainable or not. What are the challenges with this kind of a problem? Now I'll give you an example which will explain this challenge very easily. Look at it this way, that I have got two food items. One is banana and one is twinkle. Twinkle is basically a fruit bar, which exactly has the same calorific value. 3 bananas is equal to this one twinkle bar. But do you think the quality of the energy when you consume it is exactly the same? Even though the quantity of energy is exactly the same, so we need to consider the quality and suitability or substitutability of the resources. People don't really consider it. They say that this is energetically very efficient, this process is energetically very efficient, and you need to use this. But that joule of energy which you are going to utilize, that joule of energy for what it is being utilized needs to be looked into, and that's why exergy value should be obtained. That means the energy needs a certain correction which is required for the same. Right, let's move on, and I'm just giving you a certain example is the LCA, LCA, that is ecological life cycle analysis, will give you a quantity and substitutability of considering the life cycle of resources. If you have 10 to the power 6 joules of energy emitting from the sun, by the time it reaches as a fuel energy in terms of biomass or whatever it is, only 10 joules are available to you. So essentially 10 joules of fuel is equivalent to 10 to the power 6 joules of sunlight. So you can imagine what is the exergetic loss which has occurred. So must consider exergy flow in industrial and ecological system, and that is why we need to look into adopting the strategy of ecological cumulative exergy consumption to assess not only the efficiency of the process, but also the sustainability of the process. So if you look at thermodynamic matrix, you look at energy which is needed to convert feedstock into a desired product, and you calculate it in terms of return on investment. Now, if you have return on investment, you add E to it and you find out environmental return on investment. So energy which is associated with the product divided by energy which you have utilized to process that or to obtain that particular product. So energy which is retained in the product divided by energy which you have utilized. See, very similar to green chemistry and green technology which we talk about, which essentially tries to understand the carbon balance or the atom balance. If you have developed a process where every atom from the raw material gets into the product, then you have done, the atom efficiencies are very high, atom efficiency are very good. So essentially you have a sustainable process. So economic return or ecological return on investment should be more than one for being energetically profitable. So EROI of 10 indicates 10 joules produced for every joule used in the processing. So if you are developing processes in such a way that it uses energy, but the resultant product which you are having, in principle, the quality of the energy associated with it is 10 times better. Now we must think in terms of processes which are of this type. So renewability versus thermodynamic return on investment. So if you look at it, you will find that these are, on the left hand side is the renewability, and the right on the x-axis you have quality corrected return on investment. You get extremely high returns on investment, quality corrected, but the renewability is practically zero. You get newsprint essentially arriving out of wood, a wood pulp, which is a renewable sources. So we have return on investment is relatively low, but the renewability is very high. Municipal solid waste, you have return on investment 4 times and renewability is significantly high. Switchgrass, not much return you get, but the renewability is 20%. So these kind of approaches which you need to look at it when you are developing processes, especially for new products. So with this again a dilemma in terms of renewable resources. Usually non-renewable resources will definitely give you higher return on investment. Non-renewable resources can definitely never match the resources which you are using it, which are non-renewable. So if you look at, so we question ourselves whether the technology can give us the solutions. Of course, technology is the one which has allowed us to arrive at this stage and which has taught us how to develop systems, how to develop processes, how to analyze the processes. So similarly, it is also possible for us to develop this. Now here I want to mention about this thing, and I'll give you an example later on, is Jevons paradox. Jevons paradox, you develop a process. Let's say you develop a car or a car engine which works with the efficiency from current level of 30% to 50% or 60%. What would it indicate? It would indicate that people will use lesser quantity of fuel because now they have got more or higher efficient engines. But unfortunately, what happens is, because now you have got increased efficiency, the usage of car becomes more. So at the end of it, even though when you improve the system efficiency, the objective of improving system efficiency to reduce the overall resource consumption actually gets beaten, and you increase the overall resource consumption because people find that it is cheaper to use it. So let me use it more. As a result of it, the basic purpose of improving efficiency to reduce the usage of resources gets lost. So let's move on and see whether the technology is savior. So solar energy, as I said, is the only Akshay energy, that is the energy which is going to be available to us all the time, and the sustainability, of course, is unquestionable. So nanotechnology based devices, nanotechnology based products, nanotubes, usage of in variety of product. Now these synthesis, now previously when the solar electricity generation using photovoltaic cells were being utilized only for a period of with a lifetime of 10 or 15 years, somebody did the calculations and indicated in 15 years of the lifetime of the solar cell, the amount of electricity it generates, it actually uses much more electricity to make that particular photovoltaic unit. But subsequently, with the improvement in that, now we can reach up to 25% at 25 years. Now, when you are able to use the material, the same equipment for 25 years, where the amount of resources which you have used has remained the same or has in fact gone down, now you are making these particular processes sustainable. Essentially, the output should always be greater than input in terms of quality. So if you are able to make products which gives you a better quality in terms of thermodynamic analysis, second law analysis, I am sure you would have embarked upon the path of sustainability. So again, these were the issues which we have, and every time we face a new issue. In 1890s, horse dung in the street was the issue. 1910, the car was introduced and was a clean system as it was described. Increase in the number of cars resulted into Los Angeles smog, which resulted into another problem, and that resulted into tetraethyl lead being replaced by MTBE and now the ethanol. So today, if you consider US, I'm using US here because the data is readily available. Now, similar data has also been collected by us, and I can give a complete example, and last 4 decades of Indian ecosystem in terms of sustainability at some other time. So 65% of the total national oil consumption goes in transportation alone. Now you would be surprised, similarly, almost 35 to 40% of the total energy consumption of India goes in cooking alone. To feed a mass of 16% of the population of the world, which require at least 2 or 3 square meals, the quantum of energy which we use for only cooking purposes is approximately 35 to 40% of the national energy consumption. Now, do I really need to use electricity to cook this food? Definitely not. I can use biomass. But if I use biomass, how does it result into emissions of particulate matter? How does it result into an loss in the thermal efficiency? How do I consume significantly more energy? So we should come up with products or with, let's say, a solid fuel burning stove, which is as efficient as a gas stove, giving you efficiencies in the range of 65–70%, thermal efficiency, I mean. Now, if we can come up with these devices, you will be in a position to address many issues. So just as a break, yesterday this was the situation, today this is the situation. I don't know what is going to happen tomorrow in terms of the current practices. Please try to understand the fact that this is no joke. People do not realize it. If you get a chance, you read the book which has come out from MIT Press called Limits to Growth, and you'll understand they have given an example which essentially talks about a lotus which doubles its size every day. On the 50th day, it covers the entire pond. On the 49th day, it is covering only half of the pond, and we do not realize the gravity of the situation. Today, people have started realizing this gravity of the situation. So every time you develop a process, look at the sustainability of this process as well. Right, so nature of technological advances, technology has played an essential role in enhancing human being. However, there are negative effects always associated with it. Unexpected surprises is the kind of climate change and the effects which we keep on getting it. And they come as a surprise. So using thermodynamics, second law says creating order in a system must result in the greater disorder in the surroundings. Disorder often appears in the form of environmental impact. business and technologies aim to create order must result into environmental impact, which is not necessarily an advisable thing. But if environmental impact is inevitable, can we reduce it? And what are the methods which are available for us to reduce it? And that is where the concept of ecological systems and concept of circular economy or concept of biomimicry comes into picture. This is what is a typical ecological cycle. And if we can emulate this ecological cycle, I'm sure you would be in a position to, just a second. We are in a position to move towards the issues of sustainability. Biomimicry, as I said, is going to be a way to look forward to way to look into. So individual processes are very efficient. However, every available gradient, which is what is driving the process, needs to be exploited. They should be self-reinforcing, resilient network, and this is what is called industrial network systems, and I'll talk about it in a minute. Ajay Ghosh, can I take about 4 or 5 minutes more?
Yes, sir.
Yeah, okay, fine. So this is very much, so this concept is very much in contrast to the conventional industrial systems which are followed. And I'll give you an example of that. So emulating ecological systems is going to be the lead to sustainability. And it is very, very difficult to emulate that. See, look at it this way: waste is equal to food, equal to value, equal to profit. Now, these dumps, which are huge and located, let's say unscientific dumps, which are unregulated dumps, now Indian government is coming out to recover values from these particular dumps. And these dumps are being sold, they have been auctioned. And the auctioning is resulting into recovery of products from these particular dumps. These dumps are being looked at as future mines, from where the minerals can be recovered, from where the organic carbon can be recovered, which can be supplemented or used in soil. So essentially, you have a network of industrial systems, and these are the network. Standard plant, coal, water. You have a power plant, it takes up oxygen from the air, gives CO2, SO2, warm water and ash, and of course it produces electricity. Now SO2 which is being emitted, can I use limestone to convert that SO2 into calcium sulfate? Can I use that calcium sulfate to make cement, which results into water and CO2 again? I can use that cement to make concrete block plant, where I can utilize the ash, which is the fly ash, which is coming out from that. So this is an industrial network of the system. I can also bring in within this industrial network, environmental or ecological system. Same thing. You have a forest ecosystem. I have this CO2 coming out. Can I harvest this particular CO2 for CO2 sequestration? And that will result into availability of oxygen. I can use the water which is available from here as a result of water being thrown away from the civil plant to construct wetlands. If I use this fuel, water, wetland, and I can have an algal system which uses CO2. Now what this becomes now is it is not now limited to industrial system, it is industrial ecological network. So what we are trying to do is we are trying to utilize bringing in ecology, bringing in biology, bringing in chemical engineering, bringing in chemical technology. And this is the challenge for these industrial energy system or industrial network systems. So this NIS, which is essentially network of industrial systems, and need to be converted into network of ecology. Where is it? Yeah, network of industrial ecological systems. And this is where those who are not aware of is the process system engineering approach becomes extremely useful. So just to conclude in some parts, so this I have already talked about, we must look into the Indian dream. There are cultural differences between Indian dream and American dream. No point in emulating and let's say only United States of America. That is not the only country. We should be proud of our culture. We were working and living very close with nature. And I'm very happy that Kerala is one state where nature is still being governed, is still being a driving force. Now you must maintain that particular tradition. So you have systems which are economy and industry, and you need to have this circularity which is associated with it. Differential R&D operations, you are converting into industry, cost of the product, returning back, and the final demand. So this is an interaction between economy and industry, but there also exists an interaction between sustainability when you consider this and bring in the ecology. So can technology lead to sustainability? Yes, but not via the same current engineering paradigm. Technical challenges must consider life cycle to avoid shifting impacts, use life cycle to identify improvement opportunities, look at the exergy consumption or exergy destruction, design the integrated industrial ecosystems. I'm not saying that this is going to be easy, but while developing a new process, if you just keep in mind the sustainability, resource to product conversion ratios, EROI, as I said to you, you will come up with the processes which are far more sustainable. Right. So this is where I would like to conclude. Maybe I think a couple of slides are there. I would like to acknowledge Professor Bhavik Bakshi, who is a professor at Ohio State University, with whom I collaborate on this particular area, which talks about the sustainability and talks about the resource conversion to product in a sustainable manner, following the learnings from the nature, mimicking biology, which is probably the best way to achieve these particular conversions. So I would just like to thank Ajay Ghoshji and Rajan on giving me opportunity to address you all and to bring in front of you a completely new paradigm thought process, which I think CSIR should adopt while developing new technologies. Thank you very much. And if you have any questions, I'll be more than happy to answer those. Thank you.
Thank you, Rajan. We can check whether there is some echo, I think, okay, check whether anybody else, any questions to pose.
So any questions from our members? They can raise their hand. I think Dr. Nisha has a question.
Sir, thank you very much for such a wonderful presentation. It was like, as we were sitting in your classroom. Sir, I have a doubt about, this exergy. Is it like that sophistication causes reduced in exergy, reduction in exergy?
Say it again.
Sophistication that brings in reduction of exergy. If you reduce the sophistication, if you can bring down the sophistication,
it may,
for example, in the process.
No, it may or it may not. Sophistication, if you can define it in terms of energy conversion, yes. See, there are some transformations which cannot be carried out using a certain quality of energy, which need to be carried out using the same quality of energy, right? If I have an electricity, I can use this electricity, which is the highest form of energy, for all applications. But can I just use coal for, let's say, apart from heating purposes, can I use coal for anything else? If I want to use coal, let's say a steam engine, then that steam engine need to burn coal, need to produce steam, then I need to use this expand steam, generate the pressure. So all these additions will come into picture, right? For example, if I just use a solar water heater, that's the best form of energy utilization which I can have. I need not use electricity for heating water, which I'm going to use it for bathing purposes. Now, similar to you using water for the kind of processes which you use, the quality of water which you use for the processes, if you want to use water for, let's say, electronic component manufacturing, then you need an ultra pure water. That means no ions present in it, completely deionized water, right? But that deionized water is not useful for your own potable purposes. And there you require certain mineral supplements. But you can't use this mineral water for electronic components manufacture. So appropriate water usage, similar to that, you need to identify which is the lowest form of energy which can be utilized to achieve that particular conversion. If you can identify that, you have addressed the issue of exergy destruction.
Thank you, sir.
Any other questions, please?
So I like this saying of Albert Einstein very much, is the significant problems which we face cannot be solved at the same level of thinking we were at when we created them. So essentially, in my opinion, NIIST, because of the transdisciplinary research and education which is involved, is ideally suited to promote this particular viewpoint and to promote this thinking process, while each of the CSIR lab essentially is involved in developing technologies. So while you develop technologies to satisfy your industrial clients, we must also look at what is the demand from environment.
Yes, yes. Yeah. So, Rajan?
Hi, sir.
Yeah.
Hi, sir. Thank you. So, I will propose the vote of thanks. Good evening to all. Honorable Chief Guest of the Day, Professor Aniruddha B. Pandit, Vice Chancellor, Institute of Chemical Technology, Mumbai. Respected Director, beloved colleagues, dear friends, invitees and participants. It gives me a great pleasure to propose the vote of thanks on this memorable occasion of National Science Day celebration organized by CSIR-NIIST. We are extremely fortunate to have Professor Pandit, Vice Chancellor, Institute of Chemical Technology, as our chief guest for delivering the National Science Day address. So today he has given an interesting lecture on the topic, Environmental Management, Way to the Era of Sustainability. He had highlighted the importance of ecosystems and its linkages to the human being. The depletion of natural resources is faster and it's in faster rate, and it's a greater concern to us. The loss of biodiversity, increase in nitrogen cycle, and the climate change is very serious. He also mentioned that the CSIR and NIIST can contribute in the enterprise sustainability, and also he emphasized the various strategies for the sustainable growth or sustainable development. Energy efficiency, eco-efficiency, life cycle assessment, and circular economy are some of them. And it's also surprising to know from his lecture that 35 to 40% of national energy consumption goes for cooking. And overall, the sustainable technology development is the necessity and need of the time to save the economy, to save the ecosystems. So on behalf of CSIR-NIIST, I extend our sincere and heartfelt thanks to our chief guest, Professor Aniruddha Pandit, who spared his valuable time from his busiest schedule to grace the occasion. Today, we had the opportunity to hear a highly informative and exciting address. Your thoughts have enlightened our minds and encouraged each one of us. Thank you very much, sir.
Thank you, Rajan, for your kind words, and thank you for giving me an opportunity to put forward a new way of thinking at the process conversions and process system. That's all. Even if a fraction of it gets implemented during the entire thinking process of process development, I think the objective has been achieved.
So we are extremely grateful to our director for leading us in organizing this event and delivering the welcome address and introducing the chief guest. His leadership has inspired and motivated each one of us and taken the institution to greater heights. Thank you very much, sir. And we are grateful to all the head of the divisions, administrative and service sections for all their constant support for organizing the events in the lab. My sincere thanks to Dr. Jayamurthy, convener, Academic Program Committee, and all members of Academic Program Committee for their constant support in organizing the events of the lab. Our sincere gratitude to Mr. Ribin for the arrangements through MS Teams and YouTube webcast, and Mr. Kiran for all the arrangements and communication with the Chief Guest Office. Our heartfelt thanks to all the invitees, participants for attending the National Science Day program through MS Teams and YouTube online platforms. Thank you very much, sir. Thank you all.
Thank you. Thanks a lot. Thank you.
Thank you, Professor Pandit. Thank you for accepting the invitation and also delivering a wonderful talk.
My pleasure.
Thank you so much.
Thank you.
Thank you.